Supplemental math videos from Circle Christian School.
Logarithm class notes. The inverse of an exponential function. Logarithm functions are useful in modeling data that represents quantities that increase or decrease slowly. It's how we find x when it is in the exponent. Behold the great mathematician John Napier. Without him, we wouldn't be able to find that exponential number when it is a variable. Also, check out old John Napier's bones. They have some interesting things going on with them too. Okay, logarithmic functions. Just want to let you know that if you have any 3.1 questions, shoot me an email and I'll make you a nice little slide to kind of explain how the problem's done. All right, before you had the exponent was a variable, so a to the power of x equals y. The base is a, the power is x, and you got a result. Now we're just going to think backwards here. The inverse is the power equals log a, the base, and then the result. So for instance, if you have 2 to the 5th power equals 32, think log 2, or what they like to say log base 2, when you actually say it, 32, equals, what was the exponent? 5. 5 negative 1 equals 1 over 5. So therefore, log 5, or base 5, 1 over 5, or 1/5, equals the exponent, which was negative 1. The whole thing here is that we're looking for the exponent. 10 to the power of 3 equals 1,000. So log 10, which is what our calculator is actually based on here. So when you use your calculator, you're going to be using everything off of base 10. We got some change the base stuff and so forth and so on, but that's going to happen in the next lesson. Log 10, 1,000 equals 3, meaning 10 to the 3rd power equals 1,000. Properties of logarithms. Log base a, 1, equals 0. And again, you got to think a little bit backwards here. A to the power of 0 equals 1. Log AA equals 1 because log a to the power of 1 equals x. Log AX equals x because AX equals a to the power of x. This is kind of an inverse property that happens here. And if log AX equals log AY, then x equals y. This is kind of a one-to-one property. Probably the farthest stretch that we have in this whole lesson. So to solve for x, log base 2x equals log 2 base 2, 3. Therefore, the x would equal the 3. And b, to solve for x, log 4 equals x, then 4 to what power equals 4? And you go, well, 1. And again, it's a little bit of backwards thinking here. Just a note here, that anything log base a to base, log base a to a is kind of this inverse thing. It cancels out the whole log. So to simplify, log base 5, 5 to a power of something or another, because 5 to the 1st power equals 5, so log 5 cancels out at x. The big thing is here is if you have log base a to a, you are actually canceling out the log. It's got this little inverse thing going on. Okay, we're kind of dealing mostly with evaluating logarithms and graphing logarithms here. So the basic mommy and daddy of a logarithmic function is the exponent one is 2x, so therefore the logarithm one is log base 2x. Has that nice little, reflection happening here. The h's go with the x. It's telling you, hey, I'm moving left or I'm moving right. And again, because it's with the x, it has an opposite little value happening. If it's a negative h, it means it's moving toward the right. It's going to be positive. If it is a positive h, it's moving toward the left and it's got a negative value to it. K is always being added to the whole thing here, not to the little exponent, but um, it's pretty much, or I mean to the logarithm, and it's pretty much saying, hey, I'm up and down. You can use your calculator, and I know I put that down there at the time, but to tell you the truth, if I don't show you a couple of things first with the calculator here, which is better in the next lesson, you may not be able to use your calculator. You just have to make a good table of values, or, look at mom and dad and then figure out where he's uh, hanging out at. So far right and left, so far up and down. Just do the best you can do. Moving a little bit ahead, I want to talk about expanding and condensing logarithms, because when you evaluate them, old John Napier there made a whole big table, and it had to do with these special bases that work a little bit better than others, like base 2, base 3, base 5, base 7, and then pretty much after that you can multiply different things together to get the different bases. So just taking a look at it, that if you had log base a m times n, it would be log a m plus log a n. And that's because, and you got to remember that logarithms are talking about the exponents here, that base a to the power of n, m times a base a to the power of n, we add the exponents together. So that's why there's this addition with the logarithm. Log a m over n, the division or the quotient property, leg am minus leg an. And that's again because when you have a same base over a same base, we're subtracting the exponents here. And log am to a power of n just takes that power and throws it out front and says, hey, multiply me to the logarithm. And that's because when we have a base m and we're powering it up to an n, we multiply the powers here. And again, at this point, all I'm doing is just kind of exposing you a little bit to the properties here, because we're going to use them when we get in there on Tuesday. Here's the application, very famous one, the human memory model. It's a psychology class. So students participating in a psychology experiment, which is scary within itself, attended several lectures on a subject, and then were given an exam. Every month for a year afterwards, they were retested to see just what they remembered from the series. And the average scores for the groups were given by, for the function, 75 minus 6ln t plus 1, where time is anywhere between 0 months, which is the first month, of course, and 12 months. And just a reminder that the inverse of E is ln, and vice versa. The inverse of ln is E. So that's just something to put in the back of your mind. All right. So let's take a look at evaluating here when we just want to figure out their initial scores. So we have 75 minus 6 ln, 0 plus 1, which means we have this times 1. And you take your handy dandy little calculator and you end up with 6 ln 1 which ln 1, once you put it in your calculator, you find out it equals 0. So the total is 75. So now we have 75 minus 6. Oops. Oh, I can't erase it, darn it. 6 ln and 2 plus 1. So we end up with a 3 here. And again, you put it in your handy dandy little calculator. It gives you this 1 point number. So the score that they ended up with was about a 68.41. And again, just practice putting it in your calculator. You have an LN button, so just use it. And after 6 months, 75 minus 6 ln, 6 plus 1, which is of course 7. And you put it in your calculator, you end up with a 63.32. But you can kind of see what's happening here, that basically after a certain amount of time here, we start to decrease on what's happening with our exams. So here's actually the big question of the day, and I'll just let you ponder it and put it into your notes there. What does this data about the human memory model tell you about the school year, summer, and contemplate what's a better way for more successful results? Food for thought. All right. In the hurricane here, stay safe, stay well. Let me know if you need anything, and I will see you on Tuesday. Bye.